Hello, hello. Welcome all participants to this first webinar of our 2019 series of AM Focus specials. Um, First of all, let me give you a brief introduction on what we do and tell you a little bit more about our AM Focus sections. So basically, 3D BPM, the organizer of this webinar, is a specialized marketing agency for the AM industry. We help companies communicate. We help AM companies communicate their products, and we publish a number of editorial websites and properties, including 3D Printing Media Network, which you're probably all familiar with. Is a leading editorial website covering the AM industry. And we publish 3D Printing Business Directory, and we work with Smart Tech Publishing, a leading provider of market data on the AM industry on data analysis and communication. The AM focus that we do are editorial projects that we carry out through 3D Printing Media Network. What happens is basically we focus on 20 different AM industry specific topics every year. So dedicating about a 15 days to 30-day period to that specific topic. And the way we cover it is by publishing a number of articles, custom content, features, surveys, roundups, case studies, white papers, reviews, and of course, webinars such as this one on that specific topic. The first AM Focus of 2019, the topic is composites, composite additive manufacturing, and we're here to present this very fascinating segment of additive manufacturing, and which we've been researching through Smart Tech. We've recently published a report trying to analyze and explore the business opportunities around the composites, composite additive manufacturing. We're going to present these data in this during this webinar. And the way the webinar will work is we will set the concept by presenting a series of trends, data, and projections that we collected on this segment. And then we will pass the controls to our speakers, who represent what we consider three of the most important areas of composite additive manufacturing. The speakers are so we have here with us, we have Wiener Mondesir. He's the co-founder of Arevo, and he will speak in place of Mr. Bheda, who is the other co-founder. They will present their very interesting high throughput robotic material deposition technology. So high throughput, large format, high throughput deposition technologies are, we've observed that these are one of the most interesting short and medium term opportunity for composites additive manufacturing because of the benefits that composites can offer specifically for this technology. Then we have Franco Cevolini of CRP Technology. I think this is one of the most interesting companies in the entire composite additive manufacturing segment, as they develop the WindForm family of composite AM powders for powder bed fusion technologies, which is the other very interesting segment in this field. And then we have Matt Howlett. He's the president of 3DX Tech. 3DX Tech is the leading manufacturer and supplier of composite filaments for material extrusion technologies. They offer a very large selection of these materials, and they've been doing that for some time. So without further ado, let me start my presentation. There we go. Let me just activate full screen, and here we go. So the composite additive manufacturing market. This is the key points that I think emerge from this report are that the primary material, the primary reinforcement material used in additive manufacturing is carbon fiber. We've observed some other materials being used, which are especially some carbon allotropes, and the one in particular is carbon nanotubes. Also, graphene is a possibility, but there's not that much business around that at this time. The other very common reinforcement material is glass fiber in various forms. The number one application segments are automotive and aerospace. And we observed, and we are forecasting that this segment is going to grow into a 10 billion yearly revenue opportunity, growing at a 22.3 compound annual growth rate. This data includes, and we will see what exactly what this data includes, but that's 4 billion in revenues from hardware sales. I'm going to give you, of course, this presentation will be available to the participants if just contact us to receive it. We will make it available because I realize there's too much to just to read everything in the presentation. But the main points of our timeline is that the first recorded use of composites in additive manufacturing was in 2005 with the powder bed fusion systems, which is when actually WindForm was introduced in the market. I think some of the most interesting disruptions happened in 2014 when Mark Forge introduced a low-cost carbon, very particular type of technology, using actually a continuous fiber. It remains a very unique technology, but in general, that's when low-cost technologies started to adopt, composite filaments. And then in 2014, we also started to see the first large format applications, specifically the BAM from Cincinnati Incorporated technology. A very quick view at the timeline for adoption. The main points are that through 2019, the market is almost entirely based on chopped fibers for material extrusion and powder bed fusion technologies. We believe that through 22, we will see greater adoption of large format and pellet-based extrusion technologies, so very large applications, so a lot more consumption, a lot more material consumption. And then we don't expect to see continuous fiber applications in additive manufacturing until after 2023. This is to give you an idea of the overall market forecast. The main segments are hardware and parts. Material is a smaller segment. It's very interesting, but the point here is that the value is in the composite additive manufactured parts. That's where a lot of the added value is. This is just a quick overview of the difference. We expect high growth in the next 5 years. So we expect the market to go from a 1.2 billion overall market to a 5.1 billion overall market. And this is what we expect the material split is going to be in 2023. So mostly material, mostly hardware and parts. Parts includes obviously also composites and tools. Prototypes and tools, and final parts. As far as the hardware, I think these are the technologies that we see as most highly relevant. It's filament extrusion as far as commercially relevant. So filament extrusion, such as what we're going to hear from Matt, 3DX Tech. Robotic extrusion, as we're going to hear from Arevo Labs, and obviously the CFF from Mark Forge is quite relevant, and the large format technologies using pellets are very relevant, and the powder bed fusion technologies, including the material jet fusion from HP, which only uses glass bead composites at this time, is also very interesting because of the high productivity rates. This is once again the overall market forecast. Let me just go on to, I'm sorry. Okay, so this is just the technologies, and okay, so let's look at the hardware for 1 second. As you will see in this chart, by far the most important revenue opportunities represented by polymer powder bed fusion technologies, but we have to specify that this includes all powder bed fusion machines, because there are no dedicated powder bed fusion systems for composites. So it was difficult for us to split. While there are filament extrusion dedicated systems, there are not that many powder bed fusion dedicated systems, but there aren't any. So this includes all powder bed fusion systems. We do expect that powder bed fusion systems will become the largest, will become very important adopters of composite powder materials. Sorry, I don't understand why this is going back. Okay. So, this is the, okay. So which materials are we talking about? In particular, the primary reinforcements used in additive manufacturing are carbon fiber, glass fiber, known as fiberglass. There are some cases of aramid fibers, Kevlar being used, and carbon nanotubes. These are the materials that we believe have the most commercial opportunities available. How are these materials split? This report focuses specifically, our report focuses specifically on chopped fiber composite materials for thermal extrusion and laser fusion, so powder bed fusion technologies. There are some cases of thermosets being used in additive manufacturing, but those are mostly experimental technologies. They don't have a very relevant commercial application at this time. I think the most interesting segment as far as the variety of materials available is material extrusion, where we see both materials being used in the form of pellets and in the form of filaments. In both cases, they can be reinforced with carbon fiber, glass fiber, and carbon nanotubes. We see cases of this being commercially available. And we do have a number of plastics being used, which range from ABS and nylon, so more basic plastics, to now we see increasing use of high performance plastics such as Ultem and PEEK. In laser fusion technologies, we see mostly, obviously the support material is powders, and there are a lot of examples of carbon fiber and glass fiber being used in powder bed fusion, almost exclusively with nylon. As you can see here, we do have we have indicated some polypropylene also being used, and there are some reports of other more high performance materials that will be used in powder bed fusions as well. This is the split. We do expect that pellets will be the most common support because of the high throughput capabilities of large format technologies which use composite pellets, and because of the specific benefits that composites bring to large format 3D printing. Filaments are a smaller segment because obviously it's a slower technology, and powders is a quite a significant segment because it's much more established in the market today. This, as we said, this is the more specifically, carbon fiber reinforced and glass fiber reinforced powders are expected to be the largest revenue areas, because of the higher cost of the material, higher specific cost of the materials compared to pellet. But CFR pellets are expected to be the third largest revenue area because of the high throughput and the high consumption. Filaments are more fragmented. There may be less consumption of filaments compared to these materials, but a lot more different materials available. This is just to give an idea of what our forecasted CAGR is for each material type. So the most growth is expected to be in filaments and pellets, and powders is a more consolidated segment. And this is the adoption segments. This is also quite interesting, I think, because automotive and aerospace are the most interesting single adoption segments, but the other industry segment is a lot bigger. And the other industry segments in our analysis includes energy adopters, so oil and gas, and marine adopters. And these are companies that use very large parts. So the larger part capabilities that we are starting to see using composite materials will bring increasing use from these adoption segments. In this report, we also took a closer look at parts, at 3D printed parts. And okay, I don't want to go over my time. And the composite, so let's just go through this very quickly. Composite AM parts are expected to be a very significant revenue generator. We do expect them to grow into a $4 billion yearly revenue opportunity. with final parts expected to become the most significant segment. So today we think that prototypes and tools are more significant in terms of revenues than final parts, but we do expect that by the end of the forecast period, final parts, and even before the end of the forecast period, final parts will become the most important segment because of much higher numbers. We do expect them to reach a 1.8 billion, to become a 1.8 billion dollar business. Prototypes are the biggest one today. We estimate that they're worth about 300 million worldwide. This is also a more in-depth analysis of the parts. This is the types of parts that we considered, small prototypes, medium and large prototypes. And for each part, we considered a different size part to make our calculations. This is what one last chart, one chart on to highlight growth. And as you can see, final parts are expected to overtake prototypes around 2024 to become the most important revenue segment. This is, as of course, final parts are expected to have the highest growth rate at 30%, followed by tools, which we do believe will be a very, very important opportunity for composites because of several cases that we're observing now. And with this, I finish. I don't want to bore you too long with numbers. What I really want to do is I want to hear from our speakers. They all have incredibly interesting technologies, incredibly interesting approaches, and I really want to hear a lot more about what they all have to say. So I'm gonna now introduce our next speaker and pass the controls over to Mr. Mondesir. Okay, so just give me 1 second. Here you go. Okay, so Mr. Mondesir, you have the controls. I think it's probably best if you introduce Arevo and let us know a little bit about what you do.
Okay, you can hear me okay, correct?
Yes, yes.
Okay, thank you. My name is Wina Mondesir, and I am the co-founder and CTO of Arevo. Arevo is a Silicon Valley-based startup, and we are enabling digital manufacturing of composite parts. We do this through a unique blend of robotics, software, and material technology. Our materials are continuous carbon fiber and thermoplastics. We take the continuous carbon fiber in our 8-axis robotic system, spatially orients the carbon fiber in order to create complex carbon fiber structures. And these structural components are comparable to metal. So this enables OEMs to consider carbon fiber composites, 3D printed carbon fiber composites in place of critical structural applications. I want to start with a case study. This is the world's first 3D printed carbon fiber bike frame. Arevo printed this last year. We took this bike to Eurobike in Europe. It's the world's largest bike show, and it was very well received by the industry. It's a fully 3D printed carbon fiber bicycle with our technology. It's continuous carbon fiber. Hollow fibers are oriented in the appropriate fiber orientations in order to maximize the material and part attributes along the bike. If you notice the rear of the bike, there's no seat stay. It's a cantilever type design. This is unique for a bike, but only possible with 3D printing. And again, it's one piece, fully rideable, and we built one. Why this was well received by the bike community is because of many things. Today, composite bikes are manufactured using a thermoset composite process. This is very labor intensive and very expensive and messy. They start out with fabric, carbon fiber fabrics, and cut them into pieces and wrap them and prepare molds. And you end up in a curing autoclave in order to promote consolidation and get performance of fusion along the layers that you've created. And then you end up assembling and going through some quality control stage. To quote one bike manufacturer, Giant, their carbon fiber bikes, they start out with 300 some odd pieces and end up with 20 something shapes from those pieces, and it has to pass through 100 hands to finally get assembled into a carbon fiber frame. And when you contrast that with Arevo's approach, we start with digital bits, a digital model of the software model of the part, and a model of the material. We take that and we instruct our robotic cell to build the bike and orient the fibers to get the strength, and subsequently you come off the printer with a frame that's ready to ride. Why this is important is because it opens up new market opportunities for bike industry. There are about 1 million carbon fiber frames made, and carbon fiber frames average $5,000 plus dollars. Big opportunity for additive manufacturing of carbon fiber bike frames using this technology. So Arevo's approach is software, as I said, materials and robotics. So our workflow starts out with a software. The software takes a digital design and analyzes it and looks for strengths and ways to reduce the weight of the structure. It takes an analysis, and we call it additive finite element analysis, which is FEA. We threw away the traditional laminate theory approach that's used to make composites, and we tailored the approach for additive. So every single fiber is oriented in order to get the desired material property. We're able to predict and simulate and optimize the material and the fibers to get the maximum performance. The composite materials are also optimized for this process. Today, we're using a thermoplastic and continuous carbon fiber. The robotics platform is based on what we call DED, which is a direct energy deposition, employs a laser that melts the incoming filament and the substrate below, applying the appropriate pressure to produce in situ consolidation. Our properties are comparable to autoclave properties that are common today with composites. And the subsequent properties are 5x the strength and 1/3 the weight of titanium. Our manufacturing approach is really revolutionizing the way composites are done today. As I mentioned earlier, composites are very labor intensive to produce in the traditional method. With the Arevo's manufacturing cell, it's really, we consider it a lights out operation. It's a factory in a box philosophy. We take a Arevo robotic cell, and it's integrated with quality control. As we lay down every single layer, the subsequent layers that are created, a digital image, a digital twin of every single layer is created to create a representation of the part that we are able to simulate and understand and iterate and continue to improve. This is new for composites. This is new for aerospace and automotive parts. Today, you traditionally have to take a finished part and go through some sort of X-ray to understand residual stresses and micro cracks that may be present in a finished part. With our approach, we're capturing this data during the buildup of the part. The benefits of this approach is a strength to weight ratio that is comparable to high performance metals, lighter and stronger, 1/4 the cost of traditional composites. When you look at the build envelope of large format composite systems, our approach is very scalable. As you need a larger part, you can essentially put a robot on a gantry. Since we're robotics based, it's an infinite build volume. And from a deposition throughput, we're much faster than any commercial FDM-based extrusion system. And this is the key to enabling new business models, the key to actually going after applications that weren't possible. So when you look at different applications that we're looking at today, from aerospace to construction to automotive, these are some of the possible applications. Thank you.
Fantastic. Thank you so much for that presentation. That was great. There's actually a few questions, but we will get to all. Please do ask all the questions, and we will get to the questions at the end. Thank you very much for that. I heard you mention construction, and construction we didn't include in our report, but it's very interesting because we have a report specifically on construction applications of additive manufacturing. But that's great. That's definitely very fascinating technology. So let's go through all these presentations. So our next speaker is Mr. Franco Cevolini. He's the founder, the president of CRP Technology. CRP Technology is a company that really started the use of composite materials in powder bed fusion. And powder bed fusion, as far as we know, is today the most widely used technology for production. So without further ado, let me pass the controls over to Franco. Just 1 second, sorry. Okay, here we go. Okay, so Franco, you should have the controls now. And you should be able to also speak freely.
Yeah.
Okay, we hear you fine.
Okay, can you see my presentation?
Yes.
Okay, so I will speak about the use of wind form materials in CRP technologies, and as you can see here, it's something that started with the racing application and now is also available for aerospace application. This is a quick overview of our group. There are several companies. The first is CRP Meccanica, that is a company that is working with the CNC machining since more than 45 years. Then CRP Technology and CRP USA, that are the two companies that are doing additive manufacturing using SLS technologies and the wind form materials. And then Energica Motor Company, that is the company that is producing electric sport bikes. As I said before, we started with the motorsport because of where we are located. We are located in Modena, that is the motorsport Italian Valley, and so a lot of application started with this final application, with this final market in mind. So, but then after the motorsports, we were able to sorry, I lost my presentation. Can see my, sorry, hold on a second. Can you, sorry, can you read?
Yeah, I see it, we see it fine.
Because I'm not able to see anymore my presentation.
Yeah, hold on. Let me just,
okay. Okay, here we are. Okay, sorry. So after the motorsport, we were able to have several applications in the automotive. So we have used this technology for Energica Motor Company, but also for a lot of other client in the automotive industry. Aerospace, there are several CubeSat now in orbit that are using parts done by our technologies with the WindForm, drones, and also other sport applications. Yeah, we have in Italy 8 sintering machines, and we have 5 sintering machines in the United States, in North Carolina. What is important to highlight is that using the WindForm material, we were able to go from rapid prototyping to additive manufacturing. In fact, with these materials, we are now able not only to produce functional prototypes, but also final parts. So now we can call this a real manufacturing technology. We started in 2005 with the first release of WindForm XT, that is a nylon based material reinforced with short carbon fibers. And after 10 years, we released a second version of the WindForm XT, WindForm XT 2.0, that again is a nylon-based material reinforced with carbon fibers, where we are able to improve the mechanical properties and also the thermal properties that are already quite high. So now we have also another version of carbon fiber reinforced material, that is the WindForm SP. In this case, we have preferred to improve the toughness and resistance, and also this is a material that is waterproof, so it's also used for let's say application where it is very important to have the resistance to liquid and gas. These are the 2 top-level materials. So as you can see, we have a very high tensile strength and also a very high tensile modulus that is very useful. And we are talking about very light material because the density is close to 1.1. Now we have also 2 versions that are reinforced with the glass fibers. This is quite unusual because normally glass as a reinforcement for SLS application, SLS technology, is used in the form of beads, not fibers. But with this choice, we were able to improve the mechanical properties, but also the thermal resistance of the material. And most important things, talking about electric application, is that these materials are insulating, so we have no electric conduction. So, as already said, we have tons of applications. We go from motorsports to automotive to aerospace to mainly air vehicles, so drones, and medical applications. Here we can see the Ego Corsa, that is the racing version of Energica Ego or Ego, English speaking. This is a motorbike that will be used in this year for the Moto E, that is a new category that will be added to the MotoGP, Moto3, and Moto2. And the first race will be in Jerez, where we'll see our motorbikes racing in this new category. This is what I have already said. It's important to underline that all the bikes will be Energica bikes, and we were selected among other big names in the motorbike scenario. So, But we are not only using this technology and these materials for making motorsport application. We are also now able to use this technology for the production of motorbikes. Here we can see that we started with the prototype that is on the top left. Then on the top right corner, you can see the production bike. On this bike, there are a lot of parts that are still produced using the 3D printing. We are talking about the parts inside the battery pack, parts that are located around the onboard charger, and for example, the chain guard is done using again WinForm and so the 3D printing technologies. So this is very useful for us in order to be very fast and be present on the market with these models, and also it allows us to save a lot of money because obviously we are not spending money for molds or any other hard tooling necessary in the traditional technologies. Here, a very nice project that we have done 1 year ago. This is a drone that is completely done using WinForm XT, WinForm SP, and also other type of WinForm material. This is the main body, so the frame of the drone. These are the arms that are manufactured in WinForm XT 2.0. The body is in WinForm SP. So again, we are able to select the right material in order to take the most advantage for the final part. This is a motorsport application. This is an inlet manifold that is done directly in WinForm SP and so using 3D printing. And again, this is a clear example of metal replacement because traditionally this kind of part is done in casting in aluminum. And this is another very interesting application. Here we are talking about aerospace. Our materials are approved by NSA and ESA, so ESA, in order to be used in the space. So in this case, we are able to save a lot of weight and also to save space because you can take the advantage of using and so modeling what you have to produce using the 3D printing technology. Here we have some sport applications. I got Club Bheda. To be honest, here we have several technologies that are combined together because we have the body that is done in WinForm SP, but we have also the impact face that is done in titanium machine from solid by CNC, and also in other parts that are a CNC machine and then connected together. And this is a medical application, so we are talking about orthotics, and again, very useful because this is a clear example of custom production. So these are parts that are just dedicated to the single person in order to help them in what they have to do every day. So thank you for your attention. I'm sorry for the mistake in the middle of the presentation.
Thank you very much, Franco. That was great, and I think that helps demonstrate, the variety of applications that you can produce using particle bed fusion. Helps to kind of support our analysis that it is going to be a very big business opportunity. I think my personal opinion before we move on is that there is an additive manufacturing technology for each each additive manufacturing technology has its own segments and its own very significant growth potential in its areas of application. So obviously for powder bed fusion, you have certain applications, and for, as we saw before, robotic deposition, even with composite, with continuous fibers, there is a wide number of other applications that will come. And now we're gonna introduce our speaker, Matt Howlett, to look at the opportunities in terms of filament composite materials. I think once again we're going to see very different applications, but very interesting potential. So let me pass the controls over to Matt. Just 1 second, and here you go. Matt, you have the controls now, so feel free to start the presentation.
That's great. Thank you, David. Can you see my screen?
Yes. And
so the first page of the presentation?
Yes, I think you might want to make it full screen, but we see the first page. Oh no, it was full screen. My bad. Sorry.
How about that? Is that all right? How about this?
Oh, good.
Okay. So what I wanted to talk a little bit about was the composite materials that we participate in, but also a little bit deeper dive into that term carbon fiber. I'll talk a little bit about that, but here are the materials that we currently offer in the composite space. And by that, for us, it's carbon fiber based, carbon nanotube based, and glass fiber based. And each one of these in this matrix are commercial products. We have others that we either make custom for other folks or that are in development. But in each one of these grades of materials, there may be application spaces, which we'll get to, that a different type of fiber is better suited either for performance, cost, or for a specific application where a given reinforcement is more suitable than just say, the common term carbon fiber. So each one of these are materials that we've developed, have launched, and in each one of them you'll see have a little bit different type of material or carbon fiber into it for the type of application that they're going to. And just kind of dovetails in with David's presentation. Composite materials have been a major part of what we have done since we started in 2014, but that segment for us has really kind of grown and taken over the overall revenue driver in the business as we've continued to grow year over year, whether it be glass fiber, carbon fiber, or the nanofibers have really become a major part of what we do. And why we see that is the onset of adoption in primarily industrial and aerospace. The lower cost, consumer grade materials have always been popular, and they definitely sell well, but the industrial based customers and the aerospace customers are starting to really come on over the last year and a half, and really because there's more enabling technologies. And what you saw with the previous two technologies, these are mostly filament fed. They can be on a $1,500 printer all the way up to a $100,000 printer, but these more and more printers are coming into the space that can print PEEK and PEC and Ultem carbon fiber grades, and that's enabling these companies to find new spaces for these materials in their organizations and really start to roll them out to not just inside their model shops, but now we have many customers who have 15 and 20 factories, and they have cells in each one of these factories that are producing tooling and end-use parts using our materials because they finally figured out ways that they can enable their local end-use customer groups to be able to utilize these in plant. Here's a couple of pictures of some areas that we try to focus on the higher temp, higher chemical resistance, higher mechanical property applications, both when we're printing them or when we're developing materials for these markets. My background particularly is in high performance materials for many years before this. So that's kind of the area that we try to focus on is moving upline in terms of temperature and chemical. Motorcycles seems to be the theme of the day. And not to be left out here, we have a lithium-ion motorcycle that was printed. Everything on this that's polymer was printed out of 3DX Tech carbon fiber materials out of some of our aerospace grades. And this thing was dynoed out at over 125 miles an hour and actually physically ridden at about 80, 85. But it's a pretty interesting test bed for what these materials can do. And this was all printed on sub $10,000 printers. And so what I mentioned earlier about carbon fiber, the next couple slides go to, it's kind of a pet peeve, which is people always ask, hey, what percentage is your carbon fiber? And that's not really the right question. And because we kind of take a different approach to the addition of carbon fiber into our polymers, and it's based a lot on what these customer requirements are and what the market will bear for the given level of performance. So what you'll see is the consumer requirements are really cost, and then performance. Industrial grades are performance and cost, and then our aerospace customers, it really comes down to performance. And for each one of those segments, we have different materials and different carbon fibers that we employ to try to satisfy those types of needs. And the fiber sources, essentially, we have access to and we utilize what's considered in the market small tow and large tow. So the aerospace grade 24K or 12K type carbon fibers that we can use in some of our more exotic materials, PEEK and PEC and Ultems. And the large tow, the industrial grade 50K carbon fibers are what we typically use in, let's say, polycarbonate and below. You know, something a little bit more price sensitive, but these types of fibers work very well for. And also the type that you have to take a look at when you're designing a material for specific applications, whether it's going to be chopped carbon fiber or milled carbon fiber. The chopped you usually get like in the lower right picture is where we start with it. It's either a 3 millimeter or a 6 millimeter chopped. And the milled can be, you know, anywhere from 800 or 80 microns up to about 350 microns, depending on the grade that we purchase. When we're talking about chopped carbon fiber, you really have to take a look at what sizing or which fiber you're looking at for the end use. So if we're picking PEEK, for instance, we're not going to use the same chopped carbon fiber as we would use in, say, nylon 6. They're processed at different temperatures. We're looking at wetting out and dispersing in different temperatures and different types of machinery. So these types of considerations have to come into play when we're speccing out a material, and especially for a lot of our aerospace applications. And just the cost consideration, which plays into this as well. Chopped carbon fiber ranges from anywhere from $20 to $100 a kg, depending on the source and the end use. And milled is, of course, lesser expensive, and it's typically in the $12 to $50 a kg. The reason I bring this up is all these considerations have to come into play when people are specifying a carbon fiber for a given end-use application. We have grades that cover the gambit on all these. And so I just want to make sure that carbon fiber it's not just carbon fiber. And it's why I put this slide together also, which kind of explains a little bit of what we do and why we do it. These fibers are drawn to scale, essentially, where the glass fiber, the typical glass fiber that's used in composites, is about 13 microns in diameter and has about a 75 gigapascal modulus, so the stiffness. Compare that to the two carbon fibers, the 50K or the industrial grade carbon fiber. It's a smaller diameter and significantly stiffer, and even smaller diameter is 5 microns and about almost 300 gigapascals for the aerospace grade. And where this comes into play is not just cost, and so the next slide you'll kind of see the difference. But if somebody says, hey, you know, you're using 15% carbon fiber filled PEEK, some of this has to do with not just the percentage of PEEK or carbon fiber that you're using, but also which type of carbon fiber. So if you're using a stiffer carbon fiber, such as the 24K intermediate modulus aerospace grade, versus somebody else using a industrial grade 50K. What the slide on the lower right shows, that given everything equal, which never is, but say we had to pick a fiber length to do the math, with glass fiber in that composite, you're going to end up with about 1 billion fibers per kg. With the 50K, you're going to end up around 5, and with the 24 kg, you're going to end up around 10 billion fibers in that 1 kg of material. And so if you end up with twice as many fibers and each one of them are 10 or 15% stiffer, you can see that the selection of the carbon fiber really matters. And so the term carbon fiber, not all fibers are equal. And so we do a lot of work with the different materials to make sure we're selecting the appropriate material for the appropriate end-use application. And how we validate whether or not some of this is working is, we go through a lot of work and then we select competitors' materials, whether it's different peaks, different pecs, different nylons, and we print a lot of isobars here. And so we're always validating what we think we're doing is appropriate for the end use. And here's a good example of Mark Ford's Onyx product versus our Carbon X. And I think some of the work that we do on the carbon fibers and compatibilizing and mating them to the right polymers kind of shows in the end use. And that's it. I just want to do a little deep dive in the different types of carbon fibers that we use. And I guess we can open this up to questions a little bit.
Fantastic. Yes, we thank you very much for that, Matt. We do have a few questions. I think we're all okay. Can you all hear me fine? Great. Yeah. We do have a few questions from the audience. I'm gonna go through them. First of all, let me just highlight the fact that the audience can ask questions. If we will try to get to all of them. Just write them in the dedicated space. We also we will make this recording available to everybody who registered for the webinar. By the way, it's a lot of people, so this is fantastic to have such a great turnout. I guess this is a topic that is quite interesting for additive manufacturing. I think one of the reasons is because composite materials, they are really ideal materials for end use. So they are ideal materials for additive manufacturing as it transitions into an actual production technology. So let me just go through the questions. One thing that I have a question first for Mr. Mondesir. So your question was, after seeing your solution, carbon fiber started to make sense, right? But I still have a question. Is it possible to make a cross construction of the fibers? Let me activate. Okay, so you are your microphone is activated, so you are. Go ahead and answer when you're ready.
Okay, so I'm assuming the cross construction question is related to orientation, not just unidirectional. Yes. So traditionally, composites, you can do different types of ply direction, 0, 90, when you're building up a particular part. In our solution, we can orient in any direction that's dictated by software. So unidirectional, quasi-isotropic. Actually, you can have different types of layup strategies that weren't necessarily possible before.
Thank you. And there is hold on one second. There is one other question for you, Mr. Mondesir. And it's something that I also wanted to ask you. Is the type of material that you use filament or pellets or what kind of materials do you use?
So it's continuous. I wanted to draw that out. It's a continuous carbon fiber, and the resin matrix, the bike you saw, is thermoplastic resin matrix. It can be nylon. We have applications where we use a PEEK and PEC for aerospace. And that is the glue, the binder that holds it together. But it's a continuous carbon fiber. So we make our own, what we call a pre-preg. It's pre-impregnated toe of continuous carbon fiber with the polymer matrix that is fully wetted out, and we use that to deposit and robot spatially orients it in order to get the orientation at the appropriate location in the part that produces the strength or desired material property. I think you're muted.
Let me just, okay, here we go. Sorry about that. We have another question for, we have a question for Mr. Howlett. I'm sorry, we have two questions from Mr. Howlett. So let me go to the first. So what trends are you seeing in filament diameter? 175 versus 285. The user says they use 285 at work, but home projects usually run on 1.75. Oh, your microphone should be active. Okay, there you go, Matt. Matt, go ahead.
Okay. Can you hear me?
Yes, we can.
Okay, great. Thanks for that question. Yeah, that's also from the filament supplier standpoint, a fun question because there's two diameters out there, and then some people want customs. We always have to double our SKUs, and it always adds nice cost to the systems. But in general, in the U.S., it's about 80% of the business is 175. Most of the high performance, everything from say polycarbonate and above, definitely the peaks and PECs and Ultims, the vast majority of that is 175. The trend, though, is, especially for a lot of the large users, we make custom sized filament for a lot of folks. So we can make 3 that we typically don't. We could make 5 and 6 and 8 millimeter filaments for folks. But the trend is on the large parts to go bigger. But when you're printing anything under, say, 24 by 24, maybe even 36 by 36 inches, filaments work fine. You can get 150 MMS. So you're printing a pretty fast part to begin with. Anything bigger than, say, a meter, then probably filament fed isn't really the choice. Maybe large diameter filament fed, but pellets are definitely taking a share of the big meter plus size printers. But then they come with their own baggage, which is you have to have a lot of drying and conveying equipment that you wouldn't necessarily have with filament fed. So there's a lot of back end equipment that a lot of folks don't think about that come into drying and conveying and feeding pellets. The next question, sorry.
Great. Thank you very much. And I have another question for you. This time is, I'm sorry, I lost it. Let me find it again. Okay, what is your experience with print failure due to warping or lack of adhesion? And I'm guessing in particular with composite materials.
No, and you can hear me just fine again?
Yes.
That's actually a great question because if you look at the attributes, and I kind of took a slide off just to shorten it up, and I probably shouldn't have. If you look at why people add carbon fiber, you can get a lot of stiffness. The carbon fiber doesn't add tons and tons of strength. It's really about modulus. So you can design smaller parts or thinner parts and get much more strength out of it that way. But really the key is one of the big upsides is dimensional stability. So your coefficient of thermal expansion, your CTEs, drop to almost 0 when you put in, say, over 10% carbon fiber into a compound. And then on just basic $800 printers, I can print some pretty exotic materials with almost no lift and warp. We have some printers in-house where we print some materials with no heated bed at all, as long as we have a film layer where we can adhere the plastic to the bed. The addition of carbon fiber is a great enabling technology to print, say, carbon fiber peak or carbon fiber Ultim at 100, 120 degree C chamber, and you're going to make outstanding parts. And that's a very achievable chamber temp in most technologies that are available today or coming on the market. So the carbon fiber is great for modulus, it's great for electricity, it's great for a lot of things, but lift, warp, shrinkage is really one of the main benefits in terms of enabling bigger, faster parts, especially with filament fed.
Great. And I have another question, but wait, am I muted? No. I have another question, but there's no specific target. So I think this definitely applies to powder bed fusion, but probably to the other technologies as well. And the question is, besides fibers and resins, are there other consumables used in production, such as gases and solvents? And I don't know if you all want to answer. I'm going to ask this to Franco first, and then if you also want to add something else, I will ask to both of you as well.
Honestly, I don't understand very well the question because, especially for SLS, when you use the material, you are inside the chamber of the machine, and you haven't any oxygen inside in order to keep under control the oxidation of the material. So I don't understand the question about any other consumables, such as solvents. I don't understand. What we need when we process a composite material in the SLS is to be sure that we reach a full melting of the matrix in order to have the fibers or any other reinforcement inside to work properly in order to improve the mechanical properties of the final composites. So honestly, I don't understand the question.
I'm guessing maybe if there was some kind of inert gas, but I'm guessing at this point, no. The answer is no. There is no inert gas used in.
We have an inert gas inside of the chamber that is nitrogen that is used to purge the environment.
That could be. That could be. Do you use Mr. Mondesir, do you use any other materials for your technology besides the?
No. So the laser is what is promoting the fusion in our technology. The chamber is essentially the reason why we have an enclosure is really because of the laser. So it's a Class 1 laser enclosure. There is no gases required in DED. As a matter of fact, you can be in an open environment and build up structures using our technology as long as you apply the appropriate laser safety.
And I guess that would be the same for filament as well.
Yeah, the only exceptions that I would see is in the post processing of printed parts. We have some water soluble and other alkali soluble and other soluble support materials, so you can make really complex geometries. And in that process, maybe water would be the solvent, or sometimes you would have alkali, or we even have some, some pretty high-end ones where you might use acetone or some other materials to solvate the support material away. But in general, the fabrication of the part of the material itself is no specific gas or solvent used.
Okay, and I do have another question for you, since you're on the line. Is it possible, so in case of intake parts, is it possible that little fibers, as they're not continuous, could get into the engine and act as a sanding tool?
No, it's everything, all the fibers. It's a good question, because we do a lot of carbon nanotube parts too, but all these fibers are fully encapsulated in the polymer, and I would venture a guess that greater than 95% of all intake manifolds in the world are made out of 33% glass-filled nylon 6, and those fibers are encapsulated in the polymer matrix as well. So even when you're sanding parts or doing post-processing, you get part fragments. You don't get actual fibers pull out, and so we have helped customers design intake manifolds before with our materials, and it's usually a 2 or 3 part plenum that gets either glued or vibration welded together, and that kind of an issue isn't usually, or really honestly, ever at play.
Fantastic. And one other thing, also very interesting, is have you seen any need for materials that exceed peak and pack and Olton properties, e.g. with the TG, which I'm guessing is the glass transition temperature of over 300 degrees Celsius? We have had customers approach us for PEC. For instance, there's PEK, PEKK. PEK, for instance, would process north of 400 degrees in our machinery, and PBI type products and some other materials. My background's in thermoplastics, high temp thermoplastics. So if it melts, I can typically make it. Our extruders all go to about 480, our filament extruders, 480 C, so they can melt and extrude pretty much anything. But I'm also not particularly interested in cratering a $100,000 extruder for an R&D experiment. So the typical application peak and PEC, if you're moving much beyond that, there may be better ways to do it. But I'm always open to taking on new projects. It's always no unless you're asked. Fantastic. And we actually have a lot of questions now, so we'll try to get to as many as we can. But I know we kind of set 5 o'clock as as a finishing time. So we won't go over, I guess, 5:10 or 5:15 if everybody's okay with that. 5:15 my time, by the way. I know it's all different times for you. So another 10 minutes. Is that okay for all the speakers, or is that fine? Okay. So Mr. Mondesi, the question for you is: Do you have any videos of the machine in action, and how does it get started? Are you printing onto a mandrel of some kind?
No. So I do have videos. Feel free to reach out. My email address is Wiener, W-I-E-N-E-R, @arevolabs.com. So feel free to reach out. We can share content, some under NDA, some is publicly available. In terms of building up the part, we can build on existing substrates, or we can build up, it's additive, so we can build up from a build plate and build up support material and build a part on anything. But we're not per se using a mandrel. The bicycle, for instance, was a geometry that was built in 3D, X, Y, and Z orientation of the fiber, and that's not done using any mandrel. It's not a symmetrical type of shape.
Fantastic. And Franco, Mr. Cevolini, one question is about the reusability of the materials and the recycling process for composite materials. Is that a consideration, and how reusable is the material?
Well, yeah, we during the SLS process, you reach a temperature that is close to the melting point for the material that is around the part. So this is a material that could be reused for a limited number of times, and after you have to waste it, or you can also think to recycle it, maybe changing technology. So using that material, making filaments for FDM or FFF technology. That is something that we are testing right now, and it seems to something that could be done.
And one other question for you, Mr. Cevolini, is you spoke about the production, doing production on the Energica motorcycles. Do you think the SLS technology will keep supporting your production efforts, or will you be looking at other technologies and new technologies to support mass production?
Yeah, this is a good question. Depending on the numbers that we will be able to reach. Obviously, if we are talking about small parts, the break-even point with versus traditional technologies is something quite far from what. So we are not looking for any technology replacement. But talking about the big parts, obviously, after, let's say, 20, 30 parts, it's better that you consider to change the technology in order to keep under control your costs. So depending on, basically on the dimension of the part that you have to produce.
Makes sense. Thank you. And so sorry, I lost the track of where I was. Mr. Mondesi, is your business model selling the AM systems or printing parts for customers?
So our business model is parts. We manufacture parts for OEMs, but we do recognize that in order to scale, we have to create an ecosystem of partners. Those partners could include material partners that optimize materials that we can use for downstream applications. The other stakeholders in that ecosystem can include manufacturing partners, but these are existing companies that already have applications that will require continuous carbon fiber, and we can partner with them, license them the technology. But first and foremost, since we're a startup, we focus, and right now we're focused on parts and proving out the technology.
Fantastic. I would like to, so There's so many great questions, so I really don't want to interrupt, but I wanted also to have some closing remarks from all the speakers. So we'll have I'm going to have one last question for everybody, and then maybe some have a quick closing remark. So Matt, we'll start with you. Have you ever tackled interlayer bonding strength? And since we're at it, have you considered other materials? Oh no, I'm sorry. This is it. Have you tackled interlayer bonding strength?
Yes, we as part of our due diligence on a development of a material, both the fiber and the resin matrix, we do a lot of work in terms of Z strength. One of the challenges is, as a material supplier, you don't always control the machine that your customer prints the part on. So not all printers are equal. I kind of like to say, just because your printer melts plastic doesn't necessarily mean it makes parts. And so a $600 Chinese printer could maybe print a material, or extrude a material, but you're really not going to get the kind of performance you really want, or that you're paying for the material, unless you really start to build your own, or there's quite a few that we recommend for different materials. But we do have a lot of data on Z strength, and a lot of that has to do with not just the material, but also the molecular weight distribution of the material that you're using, because that can affect it. And then a lot of times you can use copolymers or blends that will melt at different rates or ranges to try to affect interlayer adhesion.
Thank you. And I don't know if you wanted to leave any closing final remarks.
From my perspective, David, thank you for pulling this together and presenting that information, and appreciate my fellow colleagues on the panel. Thank you for pulling this together.
Thank you very much. And Franco, we have one last question for you. Is there a flexible material using carbon fibers, or do you have to deal with flexibility through material thickness and, I guess, geometry?
Excuse me, could you repeat the question?
Is there a flexible material that uses carbon fiber, or do you do flexibility through thickness and geometry?
Well, so far we have two different versions of carbon fibers reinforced. The WinForm SP has an improved elasticity, so less stiffness, and in this case, playing with the shape and the geometry, you are able to, let's say, to improve the flexibility, or how the material reacts against the loads. So mainly when we use carbon fibers, it's better to work on the shape of the material, of the part.
Okay, so yes, go ahead. Matt, did you want to say something? Oh.
Just a really quick comment about that. It's a good question, because typically with the carbon fiber, you're looking to stiffen the part. And so not saying anything about 3DX, but just in general, we have carbon fiber or carbon nanotubes or carbon nanofibers that can be employed with elastomer systems, but those are typically for electrical modifications. So I don't know if the question was more geared towards achieving some type of electrical property versus a stiff elastomer, which is a little challenging. But in general, usually there's different modifiers that you'll want to put into an elastomer to try to get a different product.
Fantastic. Thank you very much. And Mr. Mondesir, if you have any final remarks, and then we can close this session.
Oh, thank you very much, David, for giving us the opportunity to speak about our respective technologies. So I want to say thank you again. And to the audience, feel free to reach out via the website, our company website, www.arevo.com, if you have questions or you're considering applications. I think that the technologies that we're developing definitely can open up opportunities for carbon fiber composites to replace metal in a lot of applications.
Great, thank you very much. And so to the audience, I wanted to say that you can, for any question, any additional question, any information request, you can reach us at info@3dpbm.com, our company website, 3dpbm.com. It's easy. It's not as hard as it sounds. I like to say it's like IBM, but it's 3DP instead of the I. So that might make it more complicated. But so 3D Printing Business Media, 3D Printing Media Network. It's pretty easy to get in touch with us. And for any questions, and if you need to get in touch with our speakers, also feel free to contact us. And if you have questions, and if you would like any presentation, just reach out. The video will become available. The recording of the webinar will be sent to all those who registered, and it will be also available on our YouTube channel as soon as it's ready. So thank you very much to everybody for participating in this first AM Focus. The next appointment for our AM Focus series is going to be on jewelry. After that, we have medical, and after that, we have 3D printed eyewear. So we do have we can also share our calendar if anybody is interested. And thank you very much, and we will hopefully we will do this again very soon. Thank you very much.
Bye.
Thank you.